And we're live now. Today's lesson, folks, will focus on finishing up some examples of those derivatives of trig functions, covering the chain rule today. And then we'll also going to spend some more time on the chain rule next time. And that's pretty much gonna wrap things up a little bit for us here with the chain rule and all these derivative formulas. We will be able to calculate essentially any derivative you can find out there that's reasonably computable. Again, there's going to be some that are slightly more complex, and you will do in calculus too. But for the purposes of Calc 1, this is pretty much it. So let's get together and let's discuss one more derivative. And I will do a derivative here, folks, that I didn't do last time, but I promised I would do today. And that is the derivative of one of those functions on the, remember, on the right side of that table. So there's a table there, and there's some formula for the left side for derivatives, and then there's a formula for the right side. And that formula is, so today's lesson, we're going to start to calculate the derivative of, and that's going to be secant x, the derivative of this function. How do we calculate that? All right. Well, here's how it goes. So first of all, let's remember that secant x is 1 over cosine x. So when we calculate the derivative, we're calculating the derivative. I'm going to write the derivative with a prime as usual, with a prime over here. In the book, by the way, they denote it, I told you last time and before that, they denote these derivatives with d over dx. There is a logic for doing so, but that logic will not be needed if you just take calculus and you'll be done. So there is a subject in math called differential equations where one does derivatives of and uses that symbol d over dx. Most people nowadays, it's kind of out of fashion. Most people nowadays would use primes. All right, so I'm going to do the quotient rule. Look here, it says 1 over cosine x. So when you do the quotient rule, you're going to say the top part prime. So 1 prime times cosine x minus 1 times cosine x prime divided by cosine squared x. And if you look here carefully, folks, if you look here, 1 prime is 0, so this product over here is entirely 0, and we are going to get -1 times, so this is 0 here, so that disappears, so -1 times, and the derivative of cosine, everybody needs to remember now, is negative sine x. And that's going to be all over cosine squared. All right, and this is going to be equal to the following thing, folks. So negative times negative is positive. So really the answer is sine x divided by cosine squared x. But that's not the thing that most people would use. So what most people would use is something slightly different, and that thing is the following. So we're going to separate this, and we're going to write 1 over cosine x here. Oops, let me write this again. So 1 over cosine x times, and there's going to be over here because, oops, let me make this smaller. So it's going to be, instead of writing here times at the bottom, what I'm going to do, I'm going to write times at the top, and I'm going to say times, and then sine x over cosine x. And if you look carefully here, this is the same as the one earlier, because 1 times sine is sine and cosine times cosine is cosine squared. But the advantage of this is that I somehow retrieve a function that I started with, this one, c1 over cosine or secant, and I can write the answer as, so this is secant and this is tangent, folks. If you notice, sine over cosine tangent. So this really is secant x times tangent x. So this is the formula that they give you on the, so secant x prime is secant x times tangent x. This is the formula that they give you on the, one of the formulas they give you on the right side of table there on page 148. I'm looking at the book, it's page 148. All right, so this is a way to calculate the derivative of a trig function applying the quotient rule. We saw the exact same type of calculation when we calculated the derivative of tangent, which, by the way, is secant squared. So everybody needs to remember that. All right, so I'm going to point out some further things, and then we'll move on from this. So if you remember, some extra things here on this lesson. So we're gonna close our discussion of trig functions with some examples. Some remarks. Let's say a remark here, because this is kind of nice to remember again. That's mostly for that class of differential equations. So if you do the derivative of sine, you are going to get cosine. And if you do the derivative of cosine, in other words, if you do the derivative of sine twice, sine prime prime, then you're going to get the derivative of cosine, which is negative sine. Right? So derivative of cosine here is negative sine. All right, if you do one more derivative, sine x, you do prime prime prime, that means the derivative of the above, that's going to be negative cosine. And finally, if you do yet another derivative, sine x prime 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 4 times here, that's going to be the derivative. So the derivative of negative cosine, which is going to be negative sine or positive sine x. So it's going to be sine x. All right, folks, and that is going to be the fourth derivative of sine, folks. It's going to be sine again. So in a way, this is a periodic process, and you might wonder, am I going to say this again, a periodic process? And I'm saying to you, yes. Unfortunately, we don't do that here in Calculus 1, but I just want to let everybody know that in Calculus 2, you will encounter the exponential function e to the x, and the derivative of that is e to the x itself. So that repeats itself constantly. Now this one repeats itself every 4 times. So if you take derivatives 4 times here, you're gonna get sine again. The same is true for cosine. So cosine prime 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 4 times is gonna be cosine again. I'm not gonna write that, so I'm just gonna leave that for you as a simple exercise if you want. It's also done in the book, so shouldn't be difficult. So that's one remark. The second remark in this lesson is that you have seen this limit before. The limit as x is, let's say, x approaches 0 of sine x over x. And on the test, I could say I was tempted to ask you a question like that, but I didn't. So, but who knows? It might be on the coming test or quiz. So the question would be, if you look at this limit, can you say that this is a derivative of something? So this is kind of going back and kind of checking again the definition of a derivative. And it's almost a gimme here because, look here, folks. So you really have a limit. Let me just put the limit here in front. You really have a limit as x approaches 0, And over here, folks, you have divided by x, and it's x itself, but it doesn't hurt to write x minus 0. Why not? So this would be something that I would be tempted to say, because it looks like a formula that I would be interested to use. How about if we say here sine x minus sine 0? Would that hurt? No, because sine 0 is also 0, so it doesn't hurt to subtract zeros. But now if we look carefully here, so this is 0 and this is 0, obviously. But if we look carefully here, this is, folks, the definition of a derivative of sine. So this is sine prime evaluated at x equals 0 and x equals 0. But what is sine prime? So sine prime, folks, we decided that was cosine. So what you see here, this limit, is nothing but cosine of 0. And that is very easy. So that is 1. That's a famous formula. That's one of those formulas that we reviewed last time when we did the review of trigonometric functions. All right, so this is the limit, and that is the value of the limit. Now, we knew this. We looked at the limit before, and we saw that, sine, when you approximate sine, we did some sort of review of that and in the section of limits. So if you look at one of the older videos, approximate sine, you're looking at the y coordinate, and that's approximately the arc length, which is x. So that's one of the reasons why we measure sine in radians. So folks, these are the two remarks that I wanted to do here, to cover here, before I do yet another example from the book that calculates a bunch of derivatives. And I'm going to do simply problem 1 here. I'm going to start with problem 1. I'm going to do a couple of problems, and then we move on to the chain rules. Problem 1 from section 2.4 says f of x equals x times x squared, times sine x. And the question says find f prime of x. And how do we find f prime of x? This is a prime example of a problem where you are forced to use a product rule. Because you cannot combine any further. You cannot distribute x squared to sine x unless you move on to Cal 2, where you will use a bunch of things called series. And yeah, those can be used and will help you greatly to kind of take care of a problem like this. But until you get there, folks, my recommendation is to stick to the product rule here. So I'm going to say PR from the product rule. I'm going to say what that is. So x squared prime times sine x plus x squared times sine x prime, right? That's what the product rule says. The two functions are this one and this one, the ones that are underlined. And this is really simple because when you do this, you will end up with 2x sine x plus x squared cosine x, and that's going to be your final answer. So that's the final answer for this particular function. So nothing really difficult, as long as you remember the basic rules, and the basic rules being the derivative of sine and cosine and tangent. Perhaps there might be, now and then there might be a question about secant or cotangent or something. You can get those formulas from the book if you don't remember those. So it would be these, and then combine them with a product rule or a quotient rule if you need. We did a bunch of examples with a quotient rule. That's with a product rule. I'm going to do yet one more example, and that example would be with a quotient rule, and that's going to be it for this lesson. So number 9 from 2.4, And by the way, folks, what I recommend that you do is when you go home and, whenever I do these problems here, I would like to think that you also try them or you have tried them or you will try them when you go home, you will watch the video, we'll pause the video here, we'll see the statement of the problem on the screen, and we'll try the problem on your own, and then watch the video, kind of play the video and see the solution. So I would like to know that you do that. I could, if I have the technology, I could ask you to work on these problems individually now for a couple of minutes before we do them here and show me your work. But again, the technology is not there, so I don't have, most likely you don't have a tablet or something to write me electronically quickly and just, kind of showing to the camera and stuff. It's just not something that I would try. So, so over here, the function f of x is, and I'm going to say what the function is here quickly. And again, so it's x divided by 2 minus tangent of x. And we want to find the derivative of that. So f prime is equal to, and that's x prime times 2 minus tangent x minus x times 2 minus tangent x prime, all divided by, and it's all divided by, so remember how the derivative quotient rule here, so the top part times the bottom minus the top and bottom prime. All right, so divided by 2 minus tangent x all squared, and that's going to be equal to, and we're going to do the calculation here. Let me increase the size of the page. How do I do that? Second, folks. Oh, there we go. All right, so this is x prime is 1, by the way, so you don't have to write anything. It's 1 times 2 minus tangent x is just that. So 2 minus tangent x minus, and the rest of it here is x times, and 2 minus tangent x prime, 2 prime is 0, tangent x prime is secant squared. So 2 minus is going to be 0, 2 prime is 0 minus secant squared x. All right, that's going to be at the top, divided by 2 minus tangent x all squared. So remember, folks, over here, 2 prime is 0, tangent x prime is secant squared. So, so that's why when you prime the 0 minus secant squared x. All right, so that's going to be equal to the bottom line. The bottom part is this one here. 1 second. So 2 minus tangent x squared. The top part is, so we got 2. We got minus tangent x. We collect the like terms if we have any. We don't really have any. Plus x secant squared x. And that is your final answer. Doesn't look pretty. Again, you shouldn't even expect the result to look pretty or even comparable to the one you started with, because this is always going to be a messier expression. So, or in 99% of the cases. So, so this is where I would leave this answer. Now, if you have questions about how to finish up some of these problems, in the book they work out further simplifications. So they say, yeah, so let's further write fractions and simplify and stuff. I don't expect that. I mean, that will be a lot of waste of time, and you kind of tend to forget about the calculus problem that you're trying to solve by just looking at those, small details. All right, so this is it for this particular lesson. If you have any questions from trig functions, derivatives, and things like that, this is a good time to let me know, because I am going to go ahead and teach the chain rule if there are no questions. All right, folks. Okay. Well, then let's go ahead.